Welcome to the exciting universe of music theory. Are you ready to learn? Then let's begin. Today we will talk about scale 3807 bajillion, which sounds like this. This scale has 10 tones, which means it is called a decatonic scale. Here are the common triads present in this scale. The diagram in the center is a graph showing possibilities for parsimonious voice leading between the triads. There are 7 major triads. There are 7 minor triads. There are 2 augmented triads. There are 8 diminished triads. Here is a Hamiltonian path of parsimonious voice leading that uses all the triads. This scale has 10 modes. The first mode is itself. The second mode is scale 3951, also known as Mathillion. It sounds like this. The third mode is scale 4023, also known as Styptillion. It sounds like this. The fourth mode is scale 4059, also known as Zilillion. It sounds like this. The fifth mode is scale 4077, also known as Gathillion. It sounds like this. The sixth mode is scale 2043, also known as Macum-Tarzanuin. It sounds like this. The seventh mode is scale 3069, also known as Macum-Shorkafzar. It sounds like this. The eighth mode is scale 1791, also known as Erigillion. It sounds like this. The ninth mode is scale 2943, also known as Dathillion. It sounds like this. The 10th and last mode is scale 3519, also known as Raga Sindhi Bhairavi. It sounds like this. The pitch class set for this scale is 0, 1, 2, 3, 4, 6, 7, 9, 10, 11. The forte class is 10, 3. This set is not prime. Imperfections are tones that have no tone or perfect fifth interval above them. This scale has 2 imperfections. They are at positions here and here. Hemitones are instances where 2 tones in the scale are a semitone apart. This scale has 8 hemitones. They are at positions here, 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 and here. Cohemitones are instances where 2 hemitones are beside each other. This scale has 6 cohemitones. They are at positions here, 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 and here. The distribution spectra describes the size of each of the scale steps, which in turn describes how evenly spaced the tones are. A generic interval is how many scale steps are between one tone and another. A specific interval is how many semitones apart they are. The generic interval of one scale step comes in 2 different specific interval sizes, 1 semitone and 2 semitones. The spectrum width of this generic interval is the highest, 2, minus the lowest, 1, which equals 1. The generic interval of 2 scale steps comes in 2 different specific interval sizes, 2 semitones and 3 semitones. The spectrum width of this generic interval is 1. The generic interval of 3 scale steps comes in 3 different specific interval sizes: 3 semitones, 4 semitones, and 5 semitones. The spectrum width of this generic interval is 2. The generic interval of 4 scale steps comes in 3 different specific interval sizes: 4 semitones, 5 semitones, and 6 semitones. The spectrum width of this generic interval is 2. The generic interval of 5 scale steps comes in 3 different specific interval sizes: 5 semitones, 6 semitones, and 7 semitones. The spectrum width of this generic interval is 2. The generic interval of 6 scale steps comes in 3 different specific interval sizes: 6 semitones, 7 semitones, and 8 semitones. The spectrum width of this generic interval is 2. The generic interval of 7 scale steps comes in 3 different specific interval sizes: 7 semitones, 8 semitones, and 9 semitones. The spectrum width of this generic interval is 2. The generic interval of 8 scale steps comes in 2 different specific interval sizes: 9 semitones and 10 semitones. The spectrum width of this generic interval is 1. And finally, the generic interval of 9 scale steps comes in 2 different specific interval sizes: 10 semitones and 11 semitones. The spectrum width of this generic interval is 1. The spectrum variation is the sum of all the widths divided by the number of tones. The spectrum variation of this scale is 1.4. Since the variation is greater than 0, this indicates that the scale is not perfectly even. The highest spectrum width is 2. Since this is greater than 1, we know that this scale is not maximally even. If every spectrum has exactly 2 specific intervals, we call that the Myhill property. This scale does not have the Myhill property. Since the generic interval ranges overlap, this scale is an improper scale. The interval vector of a scale is a description of what intervals exist between its tones. There are 8 intervals with a size of 1 semitone. They are here, 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 and here. There are 8 intervals with a size of 2 semitones. They are here, 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 and here. There are 9 intervals with a size of 3 semitones. They are here, 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 and here. There are 8 intervals with a size of 4 semitones. They are here, 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 and here. There are 8 intervals with a size of 5 semitones. They are here, 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 and here. There are 4 intervals with a size of 6 semitones. They are here, 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 and here. Each interval does not appear in this scale a unique number of times, so this is not a deep scale. This scale has reflective symmetry across an axis position 0.5 semitones from the root. This scale has a different pattern of intervals ascending and descending, so it is not palindromic. This scale has 1 ridge tone. Here, the balance of a scale depends whether the tones are spaced equally enough for the center of gravity to be in the center of the scale. This scale is not balanced. The inverse of a scale is a mirror image. It is what you get when the sequence of intervals is reversed. The inverse of this scale is scale 3951, Mathillion. This scale is achiral, since it can transform into its own reflection by a rotational transformation. This scale has no rotational symmetry. For even more detail about this scale, visit ianring.com/musictheory/scales/3807. If you found this video informative, please consider supporting this channel by becoming a patron. Of course, not everyone has the means to support a project like this one financially, and that's okay. But if you are able to spare just $1 a month, your help is deeply appreciated. It will not only allow others to continue enjoying this series for free, but will also go toward improving the quality and quantity of music theory resources we can provide. Go to patreon.com/musictheory and join others like yourselves who totally geek out on all this nerdy stuff. Thank you to these Patreon patrons.